Okay, time to start. Welcome to this very last session of Design Conference 2020 on the topic Design Education Methods. This is the second session on Design Education Method. My name is Alessandro Bertoni, and I'm Associate Professor in the Department of Mechanical Engineering at Blekinge Institute of Technology in Sweden. And I will be the chair of this session, which encompasses 5 very interesting papers, which we will listen, and we will have the chance to take and ask questions after we have watched all the presentation. Again, just a reminder, you can type your questions into the chat box while you are listening to the presentation. You can also request to actually speak and talk if you have a little bit more complex question that you know are not very eager to type into the chat box. So I will think we can start right away with the first paper. The first paper is titled Reasonable Application of Augmented Reality in Engineering Education. The presenter is Carsten Stechert, which is professor in engineering design and project management at Uppsala University of Applied Science in Germany. He has previously studied mechanical engineering in Braunschweig in Germany and in Toulouse in France. And he received a PhD from the Technical University of Braunschweig in the field of design methodology. And he was leading a design department at a railway vehicle manufacturer. Looking forward to listening to the presentation.
Hello, everybody. I'd like to show you some approach how to develop augmented reality experiences for the engineering education. Let me first explain what we define as an augmented reality experience. First of all, we have a real physical environment. This real environment is then augmented by virtual objects, objects that are generated in the computer. We do it in that way that we have a mobile device, and this mobile device films the reality. And then on the screen of the device, the combination of reality and the virtual object is shown. And what makes this augmented reality to an experience is that we can interact with this. So with the reality and also with the virtuality, can activate animations through buttons on the screen, and we can also change the viewpoint by moving the device around the real object. This is already used in industry. There are several use cases already in place. And so we thought that we can also use it for engineering education. Now we want to explain complex products and also processes. Like here you see a picture, a gearbox, and we can explain all the elements like two wheels, like the bearings and so on, to students that might not have any practical background. We can also visualize hidden information like the forces. And we can also connect then the real geometry with the abstraction that we need to understand. We also have some soft facts. So with this augmented reality experience, we have some kind of gamification of the learning outcome, and this gives us a motivation. We have also immediate feedback, because we can answer questions directly on the screen. He can use it whenever he wants. So not just in the lecture, but also in the evening or on the weekend or whenever. And this will help us to get the students keep pace with the learning outcomes. From our first tries, we experienced that we tried to put so much information in one use case that it was more confusing than helping the students to understand. And for us, it was very difficult to focus on the important things, to keep the density of new information as low as possible. And to deal with this, we developed a flow chart, and we have a 4 stages flow chart where we start with some general information, what is really the intended learning outcome of this experience. And then we go into a block where we ask some questions or answer the questions to decide if it's really necessary to do it with augmented reality or is a conventional method a better method. If we do it with augmented reality, then we answer some additional questions to set the focus. After that, we want to have a clear view on where to focus and what information we need to include and what we can exclude. And then we have the fourth block for the real implementation. And as an outcome from this flowchart, we have the concept of the complete experience, and we also have some estimation about the development hours. So how long will it take to develop this? And we have a guideline on how to evaluate the success of this experience, and we can also compare it to all the other experiences that we already developed and put in the database. Here you can see one example that was developed by using our flowchart, and you see that we have focus on the connection between the abstract blocks that you can see on the slide in the background and the 3D geometry of the moving masses that are symbolized here as virtual objects. And this was made to let the students understand on which angular velocity they need to reduce all the masses if I want to calculate a specific clutch. And this is also symbolized by the frames. Here, when I want to calculate clutch number 1, then I need to reduce on the angular velocity that is marked with the green arrow. In the end, our students gave us the feedback that it is really fun to use these augmented reality experiences and that it's really helpful to understand.
Thank you. I forgot to mention that the paper is also co-authored by Jonas, Chlebusch, and Köhler. Now we move to the second presentation, which is a paper titled Fostering Prototyping Mindset in Novice Designers with the Prototyping Planner. Paper is presented by Camilla, Arndt, Hansen, co-authored by Lasse, Skovgaard, Jensen, Ali, Gürcan, Özkil, Nuno, Miguel, Martins, Pacheco from Technical University of Denmark and from Technical University of Munich in Germany. And the presenter, Camilla Hansen, is a PhD student at DTU researching how design support can improve prototyping activities among students and practitioners.
I'm Camilla Hansen, and I would like to present the paper titled Fostering Prototyping Mindsets in Novice Designers with a Prototyping Planner, which I wrote with my colleagues Lasse, Jensen, Nuno, Miguel, Pacheco, and Ali, Özkil. It is known from existing literature that novice designers do not have the same product development competencies as experienced designers. And this goes for the prototyping skills as well. For instance, novice designers are not always aware of the range of prototype usage. They lack ability to concretize the purpose of prototyping, and they use physical models in later phases of the development process instead of throughout the development process. This is a challenge as prototyping is an essential activity in product development processes in industry. And while prototyping skills are being taught at universities, we believe that they often focus more on teaching how to fabricate prototypes than how to use them strategically. Therefore, the objective of this research was to develop a support tool to teach novice designers a prototyping mindset. By prototyping mindset, we mean that novice designers should be able to prototype for a specific purpose, and to build the minimum prototype needed to fulfill that purpose. They should understand prototyping as an iterative process and be able to identify insights and results from prototypes, as well as document and communicate these prototyping results to others. To do this, we developed the Prototyping Planner. The Prototyping Planner is a one-page template which can be used to structure a prototyping activity. A prototyping activity can be illustrated as a cycle consisting of 4 steps: think, build, expose, and act. When using the Prototyping Planner, you go through these 4 steps to plan and execute a prototype test. In the think step, you define the purpose for your prototype. In the build step, you plan how to build the minimum prototype to fulfill that purpose. In the expose step, you decide how to test or use the prototype to get the results you need. And in the act step, you evaluate results and make decisions for the next steps in the development process. Results will often spark the need for more prototype tests. Thus, the whole prototyping process can be structured through the iterative use of multiple prototyping planners. Doing this will also lead to an automatic documentation of the product development process and insights gained through prototyping. The prototyping planner was developed as part of a mechatronic product development course at the Technical University of Denmark. In 2018 and 2019, the tool was used by the student design teams to plan and structure their prototyping activities in their projects. At the end of the project, the students evaluated the effect that the prototyping planner had had on their prototyping activities through a survey. Here is an example of a prototyping planner used by a team that developed the spice dispenser that you can see on the right. The prototyping planner shows an early test which investigated that the stepper motor's position corresponded to the correct spice to be dispensed. Here we see the same team's entire prototyping process over the 3 weeks that the project lasted. When we read these 9 prototyping planners, we can follow their process and design decisions. In 2019, the 10 teams consisting of 60 people made 130 prototyping planners in total. But as can be seen here, there was quite a difference in how often each team used them. Here we see the perceived effect by the students of using the prototyping planner. Between 63 and 70% of the students agreed that the prototyping planner helped them develop a mindset for how to work with prototypes in the future, define a purpose, or evaluate results. Fewer agreed that the prototyping planner helped them recall earlier decisions or communicate. Lastly, only 23% agreed that it helped them prototype more efficiently, which was also not a direct objective. At this time, the prototyping planner has been used in 6 courses by 300 students in Denmark and Germany. We have measured different types of effects and iterated the tool based on feedback. The newest version has a slightly different format and can be downloaded from prototypingplanner.com. Currently, we are adapting the tool for industry use and developing tools that can be used together with the prototyping planner to plan the overarching prototyping process. Thank you for listening.
Thank you. And just a reminder to put all your questions in the chat box, and then we move to the third presentation, which is titled VR for Assembly Tasks in the Manufacturing Industry, Interaction and Behavior. The presenter is Yvonne Eriksson, Professor in Information Design and Vice Dean of School of Innovation, Design and Engineering, and leader of the MDH Living Labs in Mälardalen University in Sweden. She was also previous Research Director of Innovation and Product Realization, Vice Dean of the Faculty Board with response for research and research education. The paper is co-authored by Marie Sjölinder, Anders Wallberg, and Jonas Söderberg from Mälardalen University and from Riese in Sweden.
VR for assembly tasks in the manufacturing industry, interaction and behavior. The paper is written by Yvonne Eriksson, Mälardalen University, Marie Sjölinder, Anders Wallberg, and Jonas Söderberg, RISE, the Swedish Research Institute. The aim of the pilot study presented in this paper is to contribute to further knowledge on what is required from a VR application in order to be useful for the learning and planning of assembly tasks in manufacturing industry. Taking a multisensory approach to the development of a VR platform without using devices that give haptic feedback, the pilot study explored whether it was possible to simulate human perceptual cues within a training setting based on a VR environment. In order to explore how VR can be used as a learning tool for assembly and planning of a production line, a testbed was developed. The testbed environment consists of 2 tables where assembly pieces and tools are laid out. The assembly pieces constitute a simplified and scaled-down version of the cab of an excavator made by Volvo Construction Equipment. The choice of the cab model is motivated since the university own the cab models, and they do exist in 3 different varieties and are used by students in one of the civil engineering programs for training and planning of a single and a mixed assembly production line. The students practiced assembly of the 3 different varieties of the cab and found out the most efficient way to assembly, and from that they planned the takt time for every single sequence. Ethnographic methods were used for the study, including observations of participants' performance followed by individual and group interviews. Every single student received a brief instruction to the equipment, after which they used the platform for 15 minutes. During this part of the session, they assembled as much of the model as they could within this time frame. No further instructions were given, since one important aspect was to see how they approached the assembly tasks in the VR environment. The qualitative analysis was conducted by identifying themes and mapped the answer to a relevant theme. The result: all of the students had prior experience with the assembly and planning of both single and flexible product lines. When the students used the VR application, they already had experience of working with the physical cab. In the pilot study, it was obvious that the students experienced a gap between the real world and VR. This contradicts the common idea that VR duplicates the physical environment or objects and is often regarded as some kind of twin to a specific object or environment. Instead, the study confirms theories that VR is a representation of an object and or environment, meaning that visualize aspects such as appearance, relationship, and size. A VR environment exists with its own set of conditions, but it is possible to discover a relationship to the physical world. To conclude, the students participating in the pilot study gained a practical VR experience beyond a theoretical standpoint. Participating in the study provided them with a new perspective. However, the pilot study also raised new questions regarding what is required in order to move between the real world and the virtual one. What mental schemata are needed, and how can VR be used for product planning? The pilot study indicates that there is much more to be learned about how VR can be used in manufacturing industrial setting. Thank you.
Thank you. Now we can move to the fourth paper, which is titled Strategic Prototyping to Learn in Stanford University ME310 Design Innovation Course. The presenter is Lawrence Domingo, Mechanical Engineering PhD student at Stanford University under the supervision of Larry Leifer. And his current research interests are in design methodology, biodesign, and mechatronics education. The paper is also co-authored by Dylan Moore, David Sirkin, George Toye, Larry Leifer, and Mark Kutowski from Stanford University.
Good morning and good evening. My name is Lawrence Domingo, and I'm here to present Strategic Prototyping to Learn in Stanford University's ME310 Design Innovation course. ME310 is a 9-month-long mechanical engineering project-based course. Teams of 3 to 4 students are paired with an industry sponsor that provides funding and a design theme prompt for the student team. The course has existed at Stanford for over 50 years. Shown here is the project timeline students engage in throughout ME310. We acknowledge that different disciplines may focus on different pedagogical aspects of design. For example, aerospace engineering may have a focus on simulation, and computer science or software development may have an emphasis on team coordination. The methods presented are not comprehensive and may be similar and just have a different name in a different discipline. And before any prototyping begins, designers need to first understand the problem space that they are designing for. Which brings us to benchmarking. Benchmarking attempts to answer the question of what is already out there. Students are encouraged to project into the future and ask what the market may look like in 5 years. And oftentimes, students are hesitant to use the budget to purchase products for product teardowns as a benchmarking activity. In complement to benchmarking is need finding. Need finding is a learning process of discovering opportunities by recognizing gaps between how ordinary people, aka non-experts, experience the world and how the world is currently built. Need finding is more than just interviewing. It is also observation and sometimes even immersion. The goal of need finding is to gather user stories to build empathy and understand why users do what they do. Now, a key point that we'd like to make is that benchmarking and need finding are complementary methods that continue throughout the entire design process and not just at the beginning of the design process. And now I'll introduce the prototyping methods used in ME310. Critical function prototype seeks to understand the most critical, ambiguous, and contingent component of a solution idea. Students should aim to measure their CFP's functionality to establish the degree of control. Designers should prioritize the concerning aspects of a solution idea first before the more menial activities. This is difficult in practice. Novice designers are not always keen at identifying the critical function, and we get experienced designers and novice designers. However, the CFP helps ground the design process to the physical world. The CEP seeks to observe the most minimal semantic experience the user can engage in to validate a solution idea. Now, benchmarking future market trends are key. The CEP allows designers to test out need-finding assumptions quickly. Wizard of Oz prototyping is a commonly used technique where current technology is used to simulate future technology in order to quickly gain user insights and structure the technical development process. The CEP helps designers envision the future system. As an observation, difficulty identifying the critical function or the critical experience in the heat of the moment. However, many students by the end of the course can easily identify the critical function or the critical experience of a future solution idea. The dark horse prototype explores a radically divergent design space in order to learn something that is radically new. We use the term dark to connote a characteristic of something risky, radical, unfeasible, or poorly studied, where there is a high risk in future feasibility, but also a very high return in learning. Analytical techniques are important for the dark horse prototype, as they are important for contextualizing and assessing the scalability of the dark horse prototype. The funky system prototype is a medium resolution, medium fidelity hacked together prototype with interconnections held together tenuously with duct tape or spaghetti code that marks a key shift towards convergence. The funky system prototype helps elucidate system boundaries and is also the first steps towards integration. By laying out an entire system prototype, designers can determine what systems are neglected or need to be prioritized for development. And designers can also start vetting vendors to source custom-built components. The functional system prototype marks a shift away from exploration to exploitation, and the biggest difference between the funky system prototype and the functional system prototype is refinement. All hacked components are brought to a higher resolution and fidelity. Pedagogically, students learn about detailed design and good engineering. During the product development process, subsystems are in an ambiguous flux state due to component interdependency, resulting in a development impasse. Focusing on and prioritizing one critical component, Part X, helps constrain and direct the contingent specifications. Ultimately, Part X's finish will be integrated into the finished prototype or product. The final product or the final prototype is a high fidelity, high resolution prototype that is presented at the Experience Expo known as XP. Subsystems made in-house or contracted out are integrated without any hacking, and students are expected to refine their prototype's appearance, craft a narrative story that contextualizes the solution idea, and build a business case for adoption. Thank you for your time, and I hope to answer your questions.
Thank you. Now we are ready to move to the last presentation, which is a paper titled E-Learning Infrastructure Prototype for Geographically Distributed Project-Based Learning. The presenter is Stanko Šek, which is assistant professor at the Department of Mechanical Engineering at University of Zagreb. And he has written this paper together with Niccolò Beccattini, Neven Pavkovic, and Gaetano Cascini from Politecnico di Milano and from University of Zagreb.
Hi, hello everyone. My name is Stanko Škec and I'm assistant professor at the University of Zagreb. Today I'll present you a paper titled E-Learning Infrastructure Prototype for Geographically Distributed Project-Based Learning. So to explain the wider context of this study, I need to emphasize that this is part of the Erasmus Plus project, and the main aim of that project is to enhance and improve existing e-learning infrastructure used for project-based learning courses. We have 4 universities as participants: University of Zagreb, Politecnico Milano, University of Ljubljana, and TU Vienna. They together collaborate on and together have one project-based design course. So obviously we have participants from different universities which form then teams, and students have opportunity to work in collaborative multinational multicultural environment with a main goal to simulate actually this real industrial practices. It often it's the main purpose of project-based courses. So of course they're supported with industrial partner company in terms of project assignment and monitoring, tracking their progress throughout the course. So students gain a lot of contextual knowledge, but also deeper understanding of business management and other issues which maybe they're not familiar before. This e-learning infrastructure had to actually cover 3 main aspects. So one is the content aspect in terms of video recordings of lectures, tutorials, different materials, additional guidelines, PDF documents, etc. Then to facilitate and allow actually a student collaboration throughout the course by using various tools in different phases of the design project, and also to integrate educators' aspects such as monitoring and tracking progress of individual students and student teams during the course. So e-learning infrastructure actually has 3 main aspects. It's a file repository, e-learning platform, and distant communication tool. But in addition to that, we also suggested them and recommended students with tools that they might use for different aspects of design projects, so such as instant messaging, project management, concept mapping, idea sharing, and 3D CAD modeling. So besides only recommending them these tools, we also provided them with guidelines and suggestions when to use, to what extent, and for what purpose. So to validate this let's say infrastructure prototype and to implement it, we actually had 2 courses in last 2 years, but since design conference was postponed, I'll try to give you also insights, share with you insights also from this year as well. So last year we had a project with BSH, and this year with Electrolux and Rold. So how we implemented this e-learning infrastructure. So as an LMS system, we used Moodle as distant communication tool. For formal meetings, we used Adobe Connect, and as a cloud-based file repository, we used OwnCloud. But due to GDPR regulations and different regulations at different universities, we decided to use the more closed version like TU Vienna OwnCloud. In addition to that, in order to actually address various problems in design aspects, we suggest them to use Miro, WhatsApp, Slack, Trello, Microsoft Teams as well. And in terms of modeling, CAD modeling, in first year, we suggest them to use whatever they feel confident with, so such as, I don't know, tools such as CATIA, Creo, SolidWorks. But in the second year, let's say we motivated them to use collaborative 3D CAD softwares as well, such as Onshape, Autodesk Fusion, 3D Experience, in order to facilitate their collaboration due to, let's say, fast learning curve and their user friendliness. So in general, students relied even on a wider set of ICT and web tools that we suggested. We believe that this clear distinction between formal meetings and informal meetings, at least according to the feedback, help them to progress better throughout the course. As students generally express that they prefer more schematic and visual form of contents. In addition, in comparison to, I don't know, traditional long explanations, or written text, or traditional bullet points. Again, even this year we had problems with step file exchange. Despite our guidelines, there was because you need to imagine, you need to think of these teams as actually there consist of 8 team members, 4 pairs, each pair from different institution, and so some of them decided to use different tools despite our guidelines, despite our suggestions, and there were problems in order to tackle, especially in the when they had to create a final assembly. So the one additional side was that there were obviously some corrective actions needed for Moodle introduction implementation. Although it has a lot of possibilities, a lot of options, and a lot of features, students perceived it as a not very user-friendly environment, and due to that, they decided to use some other tools. Although all these different aspects were provided by Moodle as well. What was very interesting in Moodle that it has learning analytics modules, so that you can analyze actually access and what was used and in what way. This is also something that becomes more and more relevant, and I think more present in various applications. So, for example, OnShape is a very, very nice example how you can use learning analytics to analyze how students work throughout time. So, thank you very much. If you have any questions, please feel free to ask or contact me later. Thank you.
Okay, here we go with 5 presentation. I think we have listened to 5 very interesting papers which are very much related one to each other, and I feel this is very good for the session, and I see this reflect as well from the panelists asking in between themselves different questions in the chat box, which I think is highly relevant. Now we have slightly less than half an hour to discuss and pose questions. And before going into the single question that seen there, I would like to post a general question to all of you, which is actually related to the last question that was posed to Tobias Larsson in the previous keynote speech, which is, we have a lot of opportunities, and we see many interesting way and new things that teach to students, from artificial intelligence, or using augmented reality, virtual reality, key relevant importance of prototyping, all those topics that when I studied mechanical engineering were not there. And when I find myself in planning new programs or planning new educational program for students, we are often in the situation in which we have to trade off something. And what do you think about the risk of actually losing some other skills? So what should be traded off? Is there a need to trade off other subject, reduce something or something else to actually push forward this new technology, or is something that can be done complementary? Any volunteer that wants to share his opinion on this?
I can start. I'm not an engineer myself, but I see in all topics and all education programs, you always deal with this problem because it comes up new theories, new ideas, new waves of things, and you wanted to implement it in the education, but what to take away? That's a problem in general, I think. But I think it's a lot of basic knowledge you need to have still, even though there is introducing new technology. So I would say it's a tricky, and it's a challenge to find the balance between introducing new things and also to keep the basic things, which is the core of an education, I think.
Thank you.
If I may add something.
Yeah, sure.
Yeah, I absolutely agree with what Professor Eriksson just mentioned, but and I absolutely agree that there are many basic skills that still need to be taught for quite a long time. I mean, there are already a lot of attempts to try to, I don't know, apply, for example, artificial intelligence, machine learning for technical documentation, as an example. And maybe in certain amount of time, it will be possible to be enough on a certain level of maturity that it will be good enough. On the other hand, still, maybe some aspects are not on that level. So for that reason, we will probably have to wait for some time that they reach a certain level of maturity so that it can be replaced. Probably some repetitive tasks, which are done by engineers, maybe not the creative ones, not the problem-solving ones. They will be probably, they could be replaced with that artificial intelligence. But I believe that there's still a lot of things to do to reach that stage. I mean, for example, let's say in the early phase overview of patents or state-of-the-art technologies, there are already some tools, online tools, which can help you by using various machine learning algorithms to grasp some information and to get some insights in which direction you can lead your product development project. But still, there's still a lot of expertise that needs to be that is related to basic skills, as Professor Eriksson mentioned before.
Thank you. Anyone has any? Yeah, Camilla?
Yeah, I was just thinking that I think we're also seeing kind of a lot of these new engineering degrees appearing, which are much more generalized. So when I think of the engineering degrees at DTU, we have the more traditional, very specialized engineering degrees, and then we have the newer ones, which, for example, my own, which is called Design and Innovation, where they have kind of swapped these more traditional technical courses for more general product management, product development methods courses. And in a way, I feel like, at least at the moment, we need both of these types of engineers because their strengths are different. So so I feel like we need those that are very general and good at applying the technologies in a broader sense, but we also need those that really know the technical details. Yeah.
Thank you.
May I? Something I totally agree with that. So we need some special or specialists for different topics. But what also is true, we have a evolution of skills also. So in the past, there were people that are very skilled to do technical drawings with a pen. Yeah, and now you don't need these skills anymore. But you have new technologies or new techniques that you need to know. And I think it's the same here. So you will always get some new technology like augmented reality or artificial intelligence and things. You need to learn this, but there are other things that you don't need anymore. And so the curriculum will change to other skills.
Thank you. Anyone who wants to add something more, Lawrence?
Do you mind repeating the question again? I just want to make sure I actually hit your point.
It is about the fact that we have many different disciplines now that comes up as part of education, like augmented reality, virtual reality. We're talking a lot about prototyping, things that were not there a couple of decades ago, or just 1 decade ago when I did my studies. And sometimes we find ourselves in the position of needing to trade off some other topics when you actually plan for programs. So do you feel there's a need to actually to trade off, or this could be complementary, or what should be less focused in the future?
Yeah. So I've been thinking a lot about self-directed learning, and there is that trade-off. As you get better and better at something in that 24 hours of the day, you are not getting better at something else. And I think that we need to think at the university level, what brings value to the student and what things can that student focus on for themselves. And I think I think that there should be more flexibility in that depth and in that breadth, as long as that student is aware of that trade-off. I'm kind of questioning right now the need for like standards in different undergraduate level classrooms as well.
That's interesting. Thank you. Now I wish to go through the question in the chat. We'll try to address all of them, a little bit more detail on the different papers, and I take it in chronological order. So I start with the first question to Camilla from Stanco, saying, have you analyzed student performance after using the prototype planner in comparison of not using it or without using it? And what have you changed after the first version?
Yeah. In the paper that I wrote for this conference, we were focusing mostly on the perceived effect of using the prototyping planner. But after that, we have also tried to look more closely at the performance. So one thing that we've done is that we've made some sessions where we've asked students who were developing a product to make a plan for a prototype or find out what they wanted to prototype without any guidance or introduction from us. And then afterwards, we have introduced the prototyping planner and then asked them to make a plan again using the prototyping planner. And in that way, we have these two, you can say two plans or ideas for prototypes that we can compare with each other. And we are analyzing those results right now. But I think that's really interesting that we can see differences between these plans. So first of all, they tend to be quite short, at least when the students don't have this structure. And there are a lot of important questions that we see that they're missing. So for example, just identifying the purpose for their prototype, what exactly is the question they want to answer with the prototype is something that a lot of students kind of fail to define in their own planning. Yeah, and to the second question, what have we changed after the first version? So one of the things we have focused a lot on has basically just been the structure of the tool. So we've always had these 4 steps of prototyping, but in the version that I showed here in this study, we had presented these steps as a cycle. And it turned out that this created a little bit of an unnecessary confusion because some people apparently read, clockwise and some people read counterclockwise, even though we had numbers and felt like we presented that quite clearly. So in the structure that we have now, we have tried to just simplify things a lot more. So it becomes more usable to say which direction to read the paper. And then we worked with the phrasing of the questions because we use certain terms in prototyping, such as fidelity. They're quite specialized terms, and the way you try to ask students to think about fidelity, it can really influence their understanding of that phrase. So those are the things that we try to tweak afterwards.
Okay, thank you. And following up as well to this question, just Philip asking you, why such big difference in a number of planners among teams? Did all teams work on the same product or topic?
Yeah, we thought that was really interesting as well. So they all had the same topic, which was to develop products or machines to produce food. So we saw a spice dispenser in the presentation. That was also a tofu maker, stuff like that. And we saw a difference between the teams. So some teams only used the prototyping planner 5 times, and another team used them, I think, 35 times. And I think there are 2 aspects to this. One aspect is that one thing, it's actually hard to say what is one prototype and what is the next prototype. It can be very fluent between iterations. So that's a little bit of a question of how did the students see a prototype and the next prototype. But the other thing, which I think is the most important one, is kind of convincing people that this tool is supposed to help them and that it's not just a documentation tool. And I think some students perceive this as something that they would just had to do for documentation, and they felt that it was quite time consuming, as we also saw in the results. And if that's your perception of the tool, then I think they were a little less willing to use it and to really integrate it as a tool in their process. And then other teams, we saw that they really, used the tool actively and engaged with it, so they just used it much more.
Okay, thank you. This leads me to a question to Lawrence. I jump a little bit the question to Yvonne. I'll come back to that. Link actually to the use of this prototype. We have a question from Camilla about, do the students understand, which is jump away, the difference between these different types of prototype, how they and when to use what or how do you teach them these methods?
So no and yes. Initially, definitely not. Sometimes even after the week activities, still not really understood. But generally speaking, by the end of the entire year or the end of the academic year, then yes, they understand. There's usually a general understanding for why you do what. And that's one of the interesting things that comes up where initially it may not make sense at all, but by the end of the whole entire experience, then all of those parts contextualized against each other make more sense. In terms of how we teach it, we tell them the theory, realize that there's a lot of stuff that we probably missed in explaining it, and then we have them go through like a week-long project immersion and then a small group meeting. So every single week, the teaching team will have almost a one-on-one kind of crit session with the students to give them feedback. But something that kind of emerged while writing this paper is that the teaching team is not always direct about what the outcomes are, and then in the future we might try to be a lot more direct on what we're trying to get at, like what is the particular goal other than just learn something out of it.
Thank you. Did this answer your question?
Yes.
Yeah, good. Now we go to Yvonne. We got a number of questions here. The first one is from Stanko asking, can you please explain what type of introductory VR activities did the student perform?
The only introduction the student, because we thought that the students had more experience of using virtual reality than they had. Only 3 of them had experience of using it before. They have some theoretical understanding. So we gave them a very brief introduction, only how to use the equipment also, and also told them that there would be this excavator model that is transformed into a virtual reality. So that was the only instruction they got. And I think some of the students get very excited about this to use the virtual reality, but some also get nervous because they felt that they were observed in a way. And also the result indicates that it was only one that had previous experience of working with with assembly. And I think this was, if you have a long experience of assembling, then you also have to bet it was more easy for them to use the virtual reality, even if they hadn't used it before. So it was a kind of too many new things for them because they have very low experience of assembly. Does it answer your question?
I think so. Stanko's question as well. And now I have a question from Carsten, which is actually anticipating one of the questions I marked down myself. Did you think that augmented reality setup would improve the immersion of the use case?
Professor, your mic is muted. Professor Eriksson. Thank you.
I would say both yes and no, because I think the tricky thing with using this with no haptic feedback was the gravity was a problem, because if we try to implement gravity for every single detail, but it didn't work because then it's very sensitive and it fall apart all the time when you move it. So it's I don't know really. It could be worthwhile try, but I'm not sure.
Thank you. Then you have another question for you, which is from Joao Pereira, asking you, in which way should virtual reality or immersive worlds move in the future to approach real-life scenarios in manufacturing industry?
I'm not sure I understand, but if I understand the question correct, you mean that if it will be used in the future in the manufacturing industry as a kind of a learning platform, or is it the question? Yes. Yeah. But I don't know. But we have tried to make manufacturing industry interested in this. But the thing is that it's very time consuming to create virtual reality worlds. So it costs a lot of money and it costs a lot of time. So there it's hard to see where it really could be, the industry could benefit from it as it works now at the moment. If this is the answer or not, I don't know. As I think also it's still so many details to learn. And the first questions you addressed, Alessandro, I think also if you introduce a new technology, it's not only the new technology you introduce for the students, you also introduce a new way of thinking, and you also need other theoretical knowledge and skills in order to use the new technology.
Thank you. Then we have a question for Stanko as well. Did you experience the preference of the students, such as informal communication in WhatsApp, formal communication in Trello, or difference?
Yes, I mean, very good observation. Yes, definitely we did. So the main, of course, students use WhatsApp. You can actually, let's say, you can force or you can insist on maybe using some other tools, but they will use WhatsApp sooner or later. So, and we didn't. We let them choose what they want and what's more convenient for them. So, but they use the WhatsApp quite intensely. So I would say almost on a daily level. So they would create different group chats depending if they would have to swap. For example, they would distribute tasks among themselves. So they would have, for example, groups with only 2 or 3 people. Then they would have whole team chat, and then they would have another chat with the teaching assistant. On the other hand, formal communication, mostly they conducted either through Microsoft Teams or Adobe Connect, so they had formal meeting. Some teams used Trello quite intensely. Some really didn't do a lot through Trello, but I mean, it's something that probably some teams, if they picked it up early in the course, they continue using it for moderating all the process, while some others just used WhatsApp for quite intensive communication throughout the course, in addition to all the other tools that they used.
Thank you. Now I have a question myself to Carsten. It got quite interesting in the title of the paper. The first time I saw it is reasonable application of augmented reality in engineering education. So I particularly like the reasonable part. And I would like to ask you what's for you the next step for developing, I mean, a more advanced use of this augmented reality in engineering education, if it is reasonable to move further in using augmented reality in education.
Yes, I do think that it's reasonable to move further. What we experienced in the first try is that we tried to use every function that is available in augmented reality, put everything in there, and the students had too much information. They were totally confused. And so now we're developing some kind of guideline. So what information should you put in there? Are there any possibilities like to find the same objects in all the different experiences so that you don't need to learn everything new? Yeah, and then to learn the real learning intent. So not the augmented reality, use it just as a tool, but learn what it's intended to learn. So about tooth wheels, for example. And then we found out that we need to have a new methodology behind this, or take learning methods like peer instructions or things like this, and use augmented reality just as a tool, additional tool for existing methods.
Thank you. I find it particularly interesting since I'm working on developing digital twin integration in engineering education and I mean, sometimes you are in the position in which you wish to push everything into that. A lot of different things that you want to teach, and you really need to think about the reasonable application of those in the education. Good. I think we have 4 minutes left. So if there is no more question, I would like to.
I do have a question.
Yeah, sure. Perfect.
Yeah. I think it seems that we're talking about the prototypes and we're talking about VR and AR and things like that. And if you introduce these kinds of tools in education for students, there is one thing to learn to produce the tools and another thing to learn how to use it. And it could be of interest to see what's happened after when they have graduated. Will they use the tools in the way that we ask them to use the tools, or will they still be focused on creating the tools? So this is, I think this is what we have in common here, that is very complicated and complex, both to learn how to produce the tools and to use them as a tool.
I agree completely with that. I think that in the area of prototyping that I'm focusing on, there has traditionally been a high focus on teaching people, how to use the different types of fabrication technologies, how to use a 3D printer, or how to be in a tool shop. But there hasn't been the same focus on teaching. When do you use which methods? How do you do with the results you get from prototypes? All those more strategic elements of using them. So I think it serves the same focus as the technological aspects.
If I may add, I agree with both of you, and but I do think that maybe some of these things will come with time, actually. So still, I think a lot of us are searching for high, let's say, reasonable, as Carsten said, reasonable use cases for VR, for VR and AR, and in let's say in engineering education. So probably that's the direction. So after some time, if we find enough reasonable use cases, maybe we'll be able to link that to learning outcomes. Because currently, still, I believe, let's trial and error.
Yeah, absolutely.
That's very good reflections. And we have 2 minutes left. I've been reminded not to prolong this too long. So I had the last questions for all of you. If you can very briefly answer, otherwise keep your answer for yourself in reflection, which is about what's the major takeout from each of you from this session or for this conference related to what you have presented here. Did you bring home something new or something interesting points that you didn't have before, didn't thought that you had before?
I think this last discussion here was something that I will bring with me.
And I have marked a couple of things that I've seen from the conference that might be relevant for some of you in your research. You will get an email from me about suggesting papers that I see that are some similarities. Not all of you, but some of you which I have seen in other sessions. So I will spam a little bit some of you with some papers that I found in line with what we have presented. Apologize if you don't want it. Otherwise, thank you for this session. It was very good discussion, I think. And we'll meet again all together in 1 minute or 30 seconds in the stage for the closing session. Thank you very much.
Thank you very much.
Thank you.
Thank you. Bye-bye.
Thank you. Bye. Bye.